Hi everyone, thanks a lot for coming. Let's welcome our visitor Janani. She's a graduate student from University of Waterloo, advised by Professor Sapir Asadi. Janani has done amazing works in streaming algorithms, sublinear algorithms, and communication complexity. Today she'll be talking about one such work, which is going to be presented in the coming talks. And yeah, so let's welcome Janani.
Thank you for the nice introduction, and also thank you everyone for coming here. I know this is the middle of the summer and you don't have too many talks. Okay, let's start. I am going to talk about distributed triangle detection. This is joint work with my advisor, Sapir Asadi. Let's start with the model we're going to be working with. This is called the CONGEST model. There's a graph G with n vertices, and these are the n vertices. Here, each vertex is going to become a player or a node. And all the other nodes, all the players know what the entire vertex set is. The edges of the graph are going to be communication channels. So you can send messages over these edges and receive messages. And how are the edges given to these people? They only have local information. So each player only sees the edges incident to them and nothing else. So this player only knows these two edges and nothing else in the graph, and this player only knows these three edges, and so on. And how much can they communicate? Communication happens in rounds, and in one round, they can send order log n length messages over each of the edges. So over every edge, you have a bandwidth of log n, and you can send as many, whatever message you want. And you want to process this graph and minimize the number of rounds it takes to find some answer. Any questions about the model? You can stop me and ask me questions anytime. The problem we're interested in, from the title itself, yes, we're going to be talking about triangle detection. So if there is a triangle in the underlying graph, you want at least one vertex or at least one player in this game to say yes. And if there is no triangle at all, you want all of them to say no. This is what we're dealing with, and this is what they want to solve. So there are some easy, simple ways to do this. So let's just look at this vertex U. It knows these three edges. I don't think my accuracy is very good from this distance. Okay, so I'll stand here. So it has neighbors X, Y, and Z. It wants to find out if it's a part of any triangle or not. So it is just trying to find out if this edge XZ exists or XY or YZ. So if vertex U was to know the entire neighborhood of all its neighbors, it'll know if it's a part of a triangle. It can just check if any of its neighbors have an edge in common. Which means in one round, let's say vertex X chooses to send one edge to you, and then in the next round you send the other edge, in the next round you send other edges and so on. So totally, in order of n rounds, you can actually send your entire neighborhood to all your neighbors.
Which is why if you're considering the local model where you don't have the log and bandwidth limit, you can literally solve it in like
one round. It's over. Yes, it is
Ah.
very simple. So the main constraint is the bandwidth limitation.
O of n, okay. We don't have multiple edges, so.
Sorry?
No, so O of n, okay, because the degree is n, so n.
A degree is at most n all.
Okay, okay.
So, yes.
like simple graphs.
Okay, so you can solve this in order of n rounds very easily. You can actually do better. So let's look at what is known for this problem. So for randomized algorithms, Izumi and Legal gave the first sublinear number of round algorithm, and they were able to solve this in n to the 2/3 rounds. And after that, this was improved by Chang, Petty, Sarandurak, and Jiang, and they were able to get an algorithm which uses only n to the 1/3 number of rounds. And for deterministic algorithms as well, after some series of works, people were able to match this n to the 1/3 number of rounds for these restricted algorithms as well. So this is the state of art in terms of upper bounds. So both deterministic and randomized, you can do it in n to the 1/3 rounds. Okay. So let's look at what do we know in terms of lower bounds. So Abood, Senzo-Hillel, Khoury, and Lengen proved that you need at least 2 rounds. Like that's what this means. And this is for deterministic algorithms. And after that, Fisher, Gonen, Kuhn, and Oshman extend this to randomized algorithms as well. So it just says that you need at least 2 rounds and nothing else. And after that, well, there is nothing. That's it. Okay. So the upper bounds we said was n to the 1/3, and the lower bound is, it just says you need at least 2 rounds. So since people looked at a weaker model of computation, which is related to CONGEST, to try and prove multi-round lower bounds here. So let's say instead of sending order log n length messages over each edge, you can send only 1 bit. So in this weaker model, it takes at least log n rounds to simulate 1 round of CONGEST. Yes.
Like, is that 2020 and 2018? There was randomized before.
Because this is the journal version. So the conference versions of this paper came out before this.
Okay.
Then you normally cite the journal version. Any other questions? Okay. So they looked at this weaker model of computation. And here, Abud et al. In the same paper, they were able to prove an omega of log star n, lower bound for deterministic algorithms. And this was later extended to omega of log n for deterministic algorithms also. Okay. So there is nothing known even in this model for randomized algorithms. So yes, the obvious open question, can you actually get stronger lower bounds for this problem in the CONGEST model? And in this model lesson, you actually want to allow these people to send log n bits per edge and not in the just 1 bit per edge quiz. Alright, okay. There are some reasons why we haven't been able to prove very strong lower bounds here. So Eden, Fiat, Fisher, Kuhn, and Oshman, they were able to show that if you prove an n to the alpha lower bound for any constant alpha, then you're actually going to break current known circuit lower bounds. So doing this is very hard. But yes, okay. So instead of asking for these lower bounds, let's just say, can you at least try to get n to the little of 1 lower bounds? Because n to the constant we said was going to break circuit lower bounds. Okay. And this is what we end up doing. We showed that for this triangle detection problem in CONGEST, you need log n rounds for randomized algorithms also. And this is the first multi-round lower bound for the triangle detection in this model. Any questions about the result? Okay, so let's look at prior techniques, and well, this is going to be a little bit of a thing on why these prior techniques don't work. So one standard way to prove lower bounds in the CONGEST model is via communication complexity. You're going to have 2 players, Alice and Bob, and there's a 2-way channel between them, so they can send messages and receive messages across this channel. And Alice has some input X, Bob has some input Y. They want to solve this problem, some problem f of x comma y, which depends on both their inputs. And they know that this is hard, okay, in the sense of it requires a lot of back and forth communication between them. So let's say for now, they know of some problem which requires at least C bits of communication. We want to try and use this to prove lower bounds in the CONGEST model as well.
So C bits as in, how is the communication cost measured? Is it like the total number of bits communicated or max number of bits communicated by any person in a single round?
I want to say this total across this, all the
Sum of all the bits.
Sum of all the messages across like both the directions. Okay. What they are going to do is try and encode their hard problem into a graph. So I'm not going to go into specifics, but overall this is the framework. Alice had some input. Where is this gone? Okay. Alice had some input X. She is going to come up with a graph on. Yes.
Sorry, when you say hard problem, do you mean something like equality or something?
Mostly set disjointness.
Set disjoint. Okay.
Equality is easy for randomized algorithms.
Okay.
Yes. But yes, most of these things rely on set disjointness. Okay, so Alice is going to take input X and encode it as a graph. This part will only depend on X. And Bob is going to do the same thing, encode it as another graph, Y. They are going to have some edges between these graphs, but it's going to be few in number, and it's something both of them know. So they're going to try and do this. Why is this helping? They are going to make it so that this problem f of x comma y, which we said was hard, if you solve some other problem in CONGEST, okay, let's say maybe something like a four-click detection or something like that. If you solve something else, then it actually solves you f of x comma y also. Okay, so they're going to try and encode it like this. And now what? We want to see that we can actually simulate this CONGEST protocol when they construct the graph like this. So Alice is going to look at her input, look at all the nodes. She knows all the edges, like the local information for these nodes. And she knows all the edges across also, which means she can run the CONGEST protocol on her input, on her side of the graph. And Bob can do the same thing as well. He can run the CONGEST protocol on his side. So how much communication does it take? So they are going to run it and they want to send messages to each other and they'll use the two-way channel to do it. So if you want to simulate one round and there are k edges across these people, you want to send k log n length messages. Because we said each edge has a bandwidth of log n. So if you have an R round CONGEST protocol and k edges in the middle, you're going to be able to solve this hard problem with R times k log n length messages. But we said this problem required C bits, so you'll get a lower bound on R. So this is the standard way to do this. People have used this technique for, again, proving lower bounds for like K4 detection and other cliques and things. Well, why can't we apply it for our problem? And why is this hard here? So triangle detection is hard because each person has a local view. Right? There are a lot of people. You only know your neighborhood. You don't know what is going on beyond you, even in the two-hop neighborhood. Yes.
So just a point, so the neighborhood need not be fixed, right? It could also be a growing neighborhood, where people also have to simulate both nodes or something.
I don't understand the question. Sorry.
No, I mean, when you say if the neighbor if there are k neighborhoods, initially it could be something like. The nodes in the middle are not simulated by either player, and towards the end, like after a few rounds, you simulate both.
But in one round of CONGEST, all the nodes are permitted to do something. So if you want a faithful simulation, you have to actually make all the nodes do what they're doing in the original protocol.
Okay.
Okay, so you can't pick and choose, is what I'm saying. You have to follow the protocol.
So that's true, but all I'm trying to say is k need not be a constant throughout all rounds. Okay?
K as in the number of edges which were across.
Yeah.
It need not. It can depend on n. It can be poly n.
Okay.
It's fine. So yes, each person has a local view, but if you were going to split this graph only between two people, this splitting is going to give them too much information. So if you look at a triangle, at least two nodes of the triangle will be known to one of them. Okay? And to simulate this protocol, as we were saying, they must know the entire neighborhood. All edges of this node should be known to them, which means since at either one of Alice or Bob is going to know two nodes of the triangle, so they just know the triangle exists trivially. They don't even have to communicate. And they can just solve this. So any questions about this? Like why this doesn't work? Does everyone see it? All right, okay. So we said splitting it between just two people will not work. Let's just split it between three people. Okay, is this going to work or not? This is like the next question to ask. What do we do here? So we already said if there was a triangle with at least two nodes belonging to one player, then Charlie has to know the neighborhood of this vertex and the neighborhood of this vertex, so they know the triangle exists. Okay. So the only hard case here is if some triangle looks like this. And the perspective is going to be Charlie only knows these two edges and Bob only knows these two edges. Okay? So if Alice were to communicate the entire set of edges between Alice and Charlie to Bob, then Bob can solve the problem. It's just the edges between these two people that are the problem, that is unknown. Right? So what can Alice do here? She has some edges to Charlie. She has some edges to Bob. She's just going to check, okay, let me see which is fewer in number, okay, and take that fewer in number and send it to the other person. So just pick this entire set, and then you're just going to send this to Bob. Which means even like if this edge was sent by Alice, then Bob knows that this triangle exists now. Okay, so they can solve this. So if you go to any number of players, just constant number of players, if you have it, you can solve this triangle problem in constant number of rounds by just partition the players, do something. So the same thing carries through. Does that make sense? So, yes.
So, wait, the players are not doing a faithful simulation of a CONGEST protocol, or they're supposed to do a faithful simulation?
So I'm saying that whatever CONGEST protocol you have, if it solves triangle detection and you give them more information than the CONGEST protocol, they don't even need it. Okay, so there's no CONGEST protocol here. I'm trying to say that this kind of partition into people, which is like the basis of these kinds of lower bounds, is not going to work.
Okay, I see.
Because they can just solve it. So the CONGEST protocol, maybe it's doing something much more, complicated. But these people can, whatever hard problem you encode as a triangle, it's not even going to be hard.
It's not hard in sense of like communication.
Yes, it's not. Yeah, exactly.
Okay, that's what you're saying. Okay.
So we encoded a hard problem, but we were actually able to encode it as some problem. No, it was hard to begin with between Alice and Bob. I am saying in this situation, it is not hard at all.
Yeah. Okay.
So you can't hope to even find a hard problem.
Okay. Okay.
Yes.
So Alice is communicating her edges with Charlie to Bob.
Yes.
How is that a constant number of rounds?
So let's say if it's just a constant number of people, let me just divide it into 3 people. Okay, and just say in one round I'll solve these 3 people, in one round I'll solve these 3 people, and so on. So this is a constant number of groups of people. So in one round I can just say across these 3 people, see which is sparser and send it, see which is sparser and send it. So you can afford to be very, very loose, and whatever you do, if you can solve it in one round for like 3 people, you can extend this to any number of constant people.
So, like, while you're looking at whichever is sparser, does that help in the bound? Sorry, using like the O of n bits, like n bits for say disjointness and then.
I'm not thinking of this as set disjointness.
Okay.
I'm thinking of this as solving the triangle problem itself.
Okay.
So I am looking at what is sparser because I know the edges.
Okay.
And if it is sparse here, it has a fewer bit representation that I can send across the other partition because that has more bandwidth.
Okay, but that is. It might be almost equal, right?
Sure, yeah, it doesn't matter. All those, yes, yeah.
But how much communication do you need? Like, if you need to send like basically as much as the number of edges, right?
Yeah, exactly. But you have the bandwidth to do that, though. You have log n across each edge, so you can do that.
Okay, this is the part where I'm confused about. So Alice and Bob are able to communicate through their edges. That's why you're looking at the one that's like
that's sparser.
Dense, because like
yes.
so you look at the sparse edges and somehow that I think okay so the communication model is like little bit different here compared to
it is not
communication because you have
exactly.
Somehow in this model you have like multi-players. Between each pair of players there are multiple channels and each channel has a bandwidth of
log n, which is yes.
And inside whatever the player doesn't matter at all. It's irrelevant. They all have some information about the graph, and the bandwidth is the limitation. So now you want to communicate over a channel or between 2 players where you have enough channels to send all the information you want to. So you're taking the information from the sparse pair, and then just that information can be sent through the more dense channels. All right. Okay.
Yeah. Okay. So this is just supposed to be a proof of concept saying constant number of people is not going to do it.
Fair enough.
Okay, for the problem that we are looking at. So what are we actually going to do? Yes, this is like the mini conclusion after all of this. You need little omega of n players to get any super constant lower bound. And now let's go to our techniques. So we're going to take this classic ground elimination technique, which was introduced by Milterson et al. From 95, and then you take it and adapt it to this model, this point-to-point communication model of CONGEST. And the main thing we're doing is each node is a separate player. Okay, so no one person has any more information than what they actually get in the original CONGEST model. So this is the basis. There's still a lot of details that we will slowly get into. All right. Okay, so let's talk briefly about this round elimination technique. You want to start with constructing a family of hard distributions for multiple rounds. So you start with dr for r rounds. Sorry, you start with d0 for 0 rounds, and then you construct it all the way to dr for r rounds. We'll talk about how we construct these things. And then one of my professors was very fond of saying, we prove lower bounds by way of proving upper bounds. That is kind of what we're going to do here. I don't want to, yeah, okay. So let's say you assume for a contradiction that some protocol exists which solves your R-round hard distribution. You want to use this protocol to get something which solves it in R-1 rounds for the smaller distribution. So you're trying to solve the smaller distribution using a protocol for an R-round distribution. And you keep doing this repeatedly. You end up with a 0-round protocol. And if you assume that this is very, very good, you're going to assume that this 0-round protocol is doing something non-trivial that it cannot do. And this will give you the contradiction. There may be losses between like this R round to an R-1 round protocol, but these losses are something you're trying to contain. So whatever goodness you see in that R round protocol, you want to keep it and preserve it. So this is the framework. Let's start with constructing these hard distributions. Okay, so this 0-round hard distribution is very simple. You just have 3 nodes. And I'm going to say an edge exists between any pair of these nodes with probability half, independently. So a triangle is going to exist with probability 1/8. And without communicating anything, these nodes can't guess with probability better than 7/8. Okay, this is not hard to prove. And for the 1-round distribution, I am going to flood each of these vertices, the green ones, from the 0-round distribution with a bunch of useless neighbors. Okay, so we'll see why this makes it hard for them later. And for the 2-round distribution, I am going to take everything inside, which is the green and orange vertices, and flood them some more with more useless neighbors. We just keep adding other things to them. So why is something like this hard? Let's look at this 2-round instance that we constructed. Let's look at everything in the blue boxes, which is coming from a 1-round distribution. It has a bunch of useless neighbors, but it's not going to know which ones are useless and which ones are actually the 1-round instance that it has to solve. So there'll be a lot of pink vertices for these things to be very confused. And in 1 round, it will not know what should I even tell my neighbors, which is important. It has no idea. So in the first round, okay, this is useless. But what can happen is all these pink vertices know they are useless because they only have degree 1. So they can tell everyone, okay, you know what, I am not involved in the smaller distribution, just ignore me. So after 1 round, all of them disappear. You know they're useless. The useless flood vertices we added are going to be gone, which means you're left with something like a 1-round instance. And let's look at the 0-round instance. The same thing is going to happen. These people still have a lot of neighbors. They are not going to say anything useless in the first round also, like in the second round also. And after this round, the orange vertices know they are useless, so they'll be gone. So you're left with this. But we just very vaguely argued the first 2 rounds don't give you anything useful. Okay, so this is still going to be hard. And you're left with some 0-round thing, which is still, looks like you didn't really do much in the first 2 rounds, and it's still going to be hard. All right, any questions? Okay, so this was the nice, easy part, constructing the distribution. So let's formally look at how we do it for any R rounds. Start with something from the smaller dr-1, and then you add a bunch of extra vertices Okay, and the main thing is we want poly of the smaller number of rounds vertices, like poly of nr minus 1 many vertices. And then you connect each of these things to a bunch of other neighbors to confuse them. Like the flood vertices we added, just make them stars. And this is it. This is the construction of the DR distribution.
Wait, can you explain the last part again? So you said connect each inner vertex to flood vertices by stars. What do you mean? Like, okay.
I mean, they have degree, like these things have a lot of degree. The flood vertices only have degree 1. So if you just look at this, it will look like a star of outer flood vertices.
And what's the purpose of this?
So just to hide which ones are the inner vertices and which ones are useless vertices. So if you have, we're just forcing this vertex to deal with a lot of neighbors.
Wait, I mean, I thought the orange part was the part where you add flood vertices and forcing the outer vertices of the green part. So the green parts have originally some outer vertices.
Yes.
And I thought the orange part was where you flooded more vertices to kind of make the original outer vertices deal with like a lot more vertices that now they have a higher degree.
Yeah, I'm just representing the edges like this. Like it's not, the edges are not coming from here to inside this orange part. It's going from here to this orange part. It is the same thing that you're thinking. I just split it into three layers now. That's it. It's not important.
Okay.
It's okay. The perspective you have is fine. It's just there's a lot of degree for these inner vertices, and it's just this is a representation of that degree. That's it.
I see. Okay.
Yeah. Okay. Any other questions? All right. So this is the second step. We want to start with a very good protocol and construct a smaller R-1 round protocol. So how do you do this typically? Right now we're given a smaller IR-1 round instance. We want to solve this instance. And let's say we're able to embed it as some larger instance. Okay? We want to actually use the protocol for R rounds. So we construct some large instance using things we have. And then after that, we want to eliminate the first round. Okay, we don't want to use it. We want to stick with R-1 rounds. So we do some way of trying to sample what the first round messages are. We'll get into what this means in a little bit. But for now, we just want some way for these vertices to know what the first round messages are. And after that, okay, so you know what the first round messages are, then you continue from the second round. Okay. So what do we want out of these first round messages? It should be kind of accurate to what the protocol would have sent if this was the actual instance it was given. Okay, you want to be as accurate a simulation as possible. Okay, you're not actually going to get there, but you want it to be close.
And by close in sense of like close in distribution.
Yes. You want to be close. Basically, don't variation distance in distribution sense. Yes.
Okay.
Okay. So let's try this. We have a 0 round instance. Let's say we have a protocol for 1 round, and we want to use that to solve a 0 round instance. So recall this was a 0 round instance, and each edge exists independent here with probability half. So you have a protocol for this 1 round instance, which looks something like this. Okay. These were the steps. You start with some instance, and then you want to embed it as a special instance of some 1 round instance. Let's say we can do this also. Okay, you can use some public randomness and you can figure this out. Okay, I'm not going to go into this. The main hard thing to do here is to sample these first round messages. Okay. And now I'm actually going to go into the details of how to do this sampling. So yes, the main message I want you to remember is this message should not depend too much on the message that you want. Okay, it should not depend too much on the smaller instance that you want to solve. Okay, I will give you examples to hopefully convince you that if something like this happens, you can't hope to succeed. So let's start with one bad example. Okay, this vertex B is doing something that it is not supposed to. Let's say it actually sends the entire neighborhood to all its neighbors. Okay. This can't happen in an actual protocol. Let's say if it was doing something like this, okay, I want to convince you that this kind of sampling is not possible. Why? So if B was sending its entire neighborhood, at the end of the first round, the message sent by B to A is going to have information about this edge, right? Whether the edge to C exists or not, okay? But we want to sample these first rounds, right? These messages. So there is no, there should be some way for B and A to sample the first round message that B sends, but they can never do this without knowing this edge. It's not going to be accurate at all. Okay, whatever you do, you're going to be wrong, with probably at least half. Okay. So, or even maybe you could even think of it this way. When you start with the zero round instance, vertex A doesn't know what this edge is. But somehow after this first round, vertex A will know this. But this can't happen. You're not actually communicating anything. You're just sampling. Okay, this is not something that you can make happen with just sampling messages. So if some large message was sent, there is no way for you to accurately simulate this without too much losses. But the thing is, yes, if this happens, the sampling messages is not going to work. Okay, the reason is the message from B to A depends too much on this one edge, and they don't know what this edge is, and they don't have a way to do this. But yes, as we said, the message length is actually small. So this is something that will not happen. What can we do here? So this is the first attempt at sampling messages. I will talk about this, but before that, any questions? Okay, so what are we trying to do here? Vertices A and B both should know the message that B sends to A in the first round. Okay, only then they can simulate it. And we're trying to find a way so that they can sample this message. So let's say as a first step, we try and sample it with public randomness. Okay.
Public randomness as in shared randomness between everything.
Shared randomness between everyone.
Okay.
Okay, public randomness to all of them. And what is going to happen here is if this message from B to A is small, B is going to have a lot of edges, and you could somehow say that this vertex C is like a uniform random neighbor of these edges. Okay, so intuitively it's like, B doesn't know what this edge is, so it can't choose and pick information about this edge. So roughly it will contain only S over n bits of information about this edge existence. I'm keeping things very high level, but this is roughly accurate. So this is why you need small messages. Like S is very small here.
So S is like log n, O of log n.
Something like that, yes. Okay. So it looks like if you do public randomness sampling, you're not going to, you can actually sample the message which doesn't really reveal too much information about BC edge. But there is also the AB edge. Okay. So this message exists only if the edge actually exists. So they exist because they can't really send messages over nothing. So the existence of the message itself is giving you some other information that you don't know. And it is very highly correlated. So you can't use public randomness to do this. I'll wait for a little bit. You run into an immediate issue because of something like this.
Right, I don't think I completely follow this last part. So somehow your point is that if you use purely public randomness to sample the first round message, something is breaking.
Yes.
That's
exactly, yes.
So, but I don't understand what is breaking.
So if I want to use public randomness, let's say I still sample this message, okay?
Somehow using public randomness.
Sometimes this message exists, sometimes it doesn't exist. What does that mean? Sometimes the edge AB exists, okay? So they can actually send messages across this. But sometimes the edge AB doesn't even exist.
So what I was trying to understand is that, so first don't you actually sample graph for the rth round distribution? So you have like these distribution corresponding to dr minus
Yes.
1 and so on. What you have is an actual instance from distribution dr minus 1. Isn't it?
Yes, that is what you have. You have these 3 green vertices, that's it.
So yeah, so that is a dr minus 1. So don't you actually try to sample an instance first and then the message, or like I'm just trying to understand which way it goes here.
That is what you actually, most of the time it's a mix of both. You do some messages, some instance and things like that. But right now you can still think of it as, okay, some part of the instance is sampled, now I want to sample messages.
Got it. So I think the thing that is tripping me up is just like the sort of existence of an edge versus like this message. Somehow I thought it was like you first sample some instance from the hard distribution, but instead of running the protocol on that instance, somehow you're sampling a message conditioned on that graph, but you're
Yes.
not. If
That is what you want to do, yes.
But if you're conditioning on the graph, then I'm just confused about this edge existence versus not, because if you've already sampled the graph, you know exactly which
Yeah,
edges
okay.
exist, no? So
But
I'm there.
only A and B know the edge exists. C does not.
So that is not public randomness, is it?
Yeah,
Oh,
like this
so
is-
the graph is not the dr graph or graph from that distribution that you sample need not be using public randomness. When others, okay, they can't really know. They only
Yeah,
have a local
exactly.
picture anyway.
Yes.
So that is some sense it's like nobody knows actually what
No.
part exists. I see. Okay, but if you use, okay, now I understand. If you use pure public randomness, then others will some sense come to know which
Yeah, exactly.
edges exist and which not, and that somehow leads to some things
Mhm.
break. You kind of have to keep this still hidden.
Yeah, exactly.
Some
You
sense.
have to keep some things hidden. And typically, when you're using these round elimination, the messages and the inner instance don't have too much correlation. So you can use public randomness, which is like a very standard way to do this now. Okay, and this is what like a lot of these frameworks do. But here it is just not going to work for a very basic reason, because there's some partial information known only to some players, which you have to actually involve in these messages.
And somehow here, even like basically because in triangle detection, even existence of an edge versus non-existent makes a huge difference
Yes,
to your
it does.
communication. So it's something your problem cannot allow.
Yes, exactly. Yes. So
So,
Yes.
yeah, one more. So I didn't get the sampling part. So sampling a random message from a public randomness basically. So all of them have the same random bits.
yes.
How are you essentially? So are you using one more round to communicate whether it's consistent or not, or?
You cannot communicate anything. Okay, so the hope
Okay.
is you want to find a message and maybe make the rest of the instance consistent or something like that.
I see. Okay.
So you want to
So-
sample it, and later maybe you can fix some other things, do something, but no
Okay.
communication happens.
So if A and B nodes inconsistent, that is the randomness says there's no edge to A and B in some, it implies somehow.
Yes.
Then in the later rounds, you're saying they can somehow communicate to see that your initial thing is wrong, and then we can correct it.
That is not what I am saying at all.
Okay.
Okay, I think maybe we can take this off. Like
Okay.
they only have one round to sample. They're not
Yeah.
communicating anything, and they want to make this as accurate as possible. And all I am saying is this way is not going to cut it.
Okay. Okay.
This
Okay.
public sampling, which is like a common thing to do, is not going to work here at all.
Okay.
So let's do a quick recap of what we're trying to do. We're trying to use this round elimination technique. These are the major steps. We did these first 2 steps, and we're trying to solve the 0 round instance. And we want to sample these first round messages. And the first attempt at sampling these messages failed. We used public randomness, and it failed because of correlation of this message with the underlying edge. Okay. And what is the next attempt we're going to do? This is something that was touched upon briefly. You can't use public randomness to this, but only vertices A and B should know this message. No one else needs to know. So we're introducing something called pair randomness between these 2 vertices. Okay. And basically each pair of these vertices has their own private source of randomness that only they can see. This is not all the pairs, but let's just assume like, okay, it's true here. So you sample the message that B sends to A with this new source of randomness between them, and you can sample them only if the edge exists. Both of them know this edge's existence, so they can sample conditioned on what is happening inside them. Okay? And the earlier logic that we saw, that B has a lot of neighbors and doesn't send information about this BC edge, is still true. So whatever message you sample with this pair randomness is going to reveal very small information about this BC edge. Okay, you've done something. Now what? You can actually repeat this to figure out the message from B to C as well. Use the source of randomness between these two vertices. And you sample this message only if the edge exists. And then this message is also going to reveal only very little information about the edge to A. Okay? So only S over N information roughly. So it looks like we are definitely making progress. But, well, the next attempt is also going to fail. Does someone see why? It is again for a very dumb protocol. So let's say vertex B is doing something very stupid. It is going to send the same message to all its neighbors. And it doesn't differentiate at all. Okay. If this happens, then your approach is going to completely break down again. Because with vertex B to A, you sampled something. It has to be the same thing that you're sampling across this edge as well. But how do they know? They can't do that. Vertex A doesn't know what is going on here. Vertex C doesn't know what is going on here. Okay.
Oh, are you saying that if you use only pair randomness, you can't simulate certain kinds of messages that can be sent in a first round protocol? And a simple example is like, let's say the first round, the protocol is such that just B sends the same message to everybody.
You're not putting any restrictions on the protocol. Whatever it does, you want to actually simulate it.
But in that case, how would you... Okay, I'm just puzzled how with... Okay, why can't we have like person and all their neighbors share some randomness, and another thing again, a vertex and all its neighbors share... that would fix this, no? Or
you're doing something more complicated than what we did to fix it, but you can fix it. Yes. We haven't gotten into how we're fixing it.
Alright.
Okay. So this is the second attempt, and when we did all of this, it is failing because messages are not consistent. Okay. And yes, the second attempt with pair randomness failed because of correlation between the messages themselves. What actually ends up working is you need to do a combination of both. Okay. So let's see why. So if B was doing the stupid thing and sending the same message to everyone, this message is still going to contain only low information about specific edge AB and edge BC. Yeah, because B still didn't know which are the special neighbors. And so let's just sample some messages outside of these green vertices publicly. So why can we do this? Everybody knows that B is going to have some neighbors outside, no? Only this edge is something we're revealing to everyone. And this is fine, you can do that. Everybody just knows that B has some outside neighbors, and we're sampling the message that B sends to these neighbors with public randomness. So in a very vague way, what this will do is whatever is common between the two messages from B to A and from B to C, it kind of fixes that. Okay, if there is some common randomness that B is using, that part is going to be fixed now and not cause any issues of multiple different ways of sampling. Okay. Again, I'm not going to go into too much details, but intuitively this is why it helps. So this is the final attempt. You have to sample some messages outside with public randomness. And inside the instance, the green vertices, you have to sample with pair randomness based on the edge existence and based on what you did publicly. Okay? And everything else, we can just figure it out with private randomness. Yes?
Like, everywhere, how do you distinguish between the red and green edges? You red and blue edges?
So the red edges are like you're starting with a smaller round instance. No, the red edges are the edges inside that instance.
Okay.
Okay, and the blue edges are the things that you said, okay, I will take these vertices as a part of the bigger instance, and you said that, so you kind of know.
Okay.
It is to other neighbors you're actually
Okay,
running.
because it's our construction, we know which are the
Yeah,
next.
exactly.
Okay,
because
okay,
it's
okay.
your construction only. You added these orange vertices to the
I
thing.
see.
Any other questions? All right, okay. So this is going to end up working, and mainly because there's a lot of neighbors which mask whatever difference you're going to have. And yes, okay, I'm going to conclude now. I'm not going into more details. Yeah, okay. So as we said, we use this round elimination technique, and the main challenge was messages have a lot of low correlation with the smaller instance, but now that is not true in the problem. You have to do something very specific because we're dealing with two heavy kinds of correlation. The first thing was messages correlated with the underlying edge, and the next thing was messages are correlated with each other. So we're doing like a long sampling step to deal with both of this together. And this is the main technical contribution. We gave this multi-step sampling process on how to deal with this correlation using like a lot of information-theoretic tools. And the final result is round complexity of this problem in CONGEST is omega of log n rounds. And the technique we used was this round elimination, which is adapted for these point-to-point CONGEST.
So one question I had was like, where does the log n come from in the sense of like, okay, so you're doing these round eliminations, somehow you're saying that only up to like log n rounds, somehow everything you're doing is working. Is this something to do with like success probability and stuff? Like if you have more rounds, somehow something you're losing that you're not able to get all the way. How do I understand
Yes.
where
Okay,
this limitation is right now?
I was going to go into this late, but okay, yeah. So the main thing is when you're adding these new flood vertices, you have to add poly many of them.
Okay.
Okay. So this poly many of them is necessary because you have to deal with this distance between the distributions and you have to keep it small. So you need these poly many of them to mask whatever is going on, whatever changes you get. And this polynomially, like usually if something grows polynomially, you do it in log n rounds.
Okay.
Right? So you start out with, like the actual result we prove is if you have r rounds, you need n to the 1 over 2 to the omega of r kind of communication.
Say that again. If you have R rounds.
If you have r rounds, like it's not just saying you need log n rounds in CONGEST. The final result will say if you have specific r rounds in the CONGEST model, then the bandwidth is omega of n to the 1 over 2 to the order of r.
Okay.
Okay, so this kind of growth you get because of this polynomially many flood vertices. If this polynomial is something you can reduce, then you'll get a better bound.
Interesting.
But right now we don't know how to do that. So there are still obviously like a lot of open questions. And yes, the main one is, can you get something better than what we did? Can you get it to log n lower bound also, or even something better? And if you prove omega of n to the alpha for any constant alpha, you are going to break semi-lower bounds. So n to the little lower bound, okay? So it's fine. Log n is still okay. For other cliques, there are still problems which are open. For p larger than 4, to detect the kp clique, there is an upper bound of n to the 1 minus 2 over p. And there's a lower bound of omega square root n over p for any p less than square root n. So this is not tied for any, like starting from 5. 5 cliques is still open. And that's it. Any other questions?
Any questions for the speaker? I think I asked a lot of questions. So circuit lower rounds, maybe, I can ask one more if no one else is asking. So in terms of like circuit lower bounds, could you be a little bit more specific on like what kind of circuit lower bounds we will end up proving? I'm just trying to understand, is there a problem in circuit complexity that is sort of directly connected to time detection that I can think of. I'm not able to imagine.
So there is no standard problem. Like most of the time, you don't know explicit problems for which you can prove strong lower bounds. No. Here, what you can actually do is just detecting if there's a triangle or not. This is in polynomial time, yes. And this is a problem that you can actually prove a lower bound of superlinear size lower bound on log n depth circuits.
Oh, I see.
Okay, so
I
if
see.
you can prove omega of n to the alpha or something, then you'll prove like omega of n to the 1 plus some function of alpha-ish kind of lower bound of the size of log n depth circuits.
So there is some sort of a direct reduction where if there is some problem, and that not like a standard circuit complexity problem, but like some triangle detection kind of problem where if you're able to build a circuit for that, then somehow that implies a CONGEST protocol, and which is why CONGEST lower bound implies something.
Yeah, exactly. So what is happening is these kinds of models, you can actually simulate circuits. You can run circuits using these kinds of like CONGEST model itself after doing some kind of decomposition, blah, blah, blah. Okay. So since you can simulate circuits, the lower bound here is going to give you a lower bound on circuit size also.
Wait, sorry. You're saying the lower bound here breaks the circuit lower bound there. Oh, because
It's
the
going
lower
to give you
bound.
like a stronger lower bound on the size of circuits.
Okay, so that's what you mean by
Yeah.
break circuit lower bound.
Like right now, I think for log n depth circuits also we can prove 3n something. I'm not keeping track of constants. I know 3 is like the big number. Okay? So you'll prove like n to the 1 plus function of alpha, which is superlinear. So we can't do that. Okay. Yes, sounds good. Thank you.
Thank you. Thanks.